Hi students, this is Data Herbology Physics faculty. Here I would like to give a lecture on optical fiber. In this video, I explain about the losses of optical fiber. Now, first of all, you should learn about what is attenuation. Generally, when the signal is passes through the optical fiber due to the various losses, the signal it should be changes. Suppose when you are observing this diagram, so this is the sending signal. After traveling through the optical fiber, it is changes due to various losses. This is called attenuation. So attenuation is the change in signal when it is passes through the optical fiber. So the optical signal attenuated progressively in the fiber due to various losses. Now the attenuation coefficient alpha can be written as alpha is equal to minus 10 by L. Sorry, here this is plus 10 by L log base 10 P in by P out. Units are decibels per kilometer. Here P in is the input power, P out is output power, and L is the length of the optical fiber. So by using this we are calculating what is the attenuation when the signal is sending through an optical fiber from one place to another place. Generally the loss of signal we are measured in decibels. It can be written as P in decibels minus P out decibels, the input power minus the output power. It should be represented in decibels. And here there is a formula. This formula, by using this formula, we can convert the power into decibels, power in decibels, and the power in decibels you should convert it into milliwatts. So by using this formula you can easily convert it from milliwatts to decibel meter and decibel meter to milliwatt. This is very important formula, but it is not in our syllabus. No problem. Now fiber losses. The losses occurring fiber may be mainly due to absorption losses, scattering losses, and radiative losses. Absorption losses due to the presence of impurities in the fiber. In the preparation of optical fiber, by default it consists of OH minus ions. These ions caused electronic dispersion of light at wavelength 0.95 micrometers and 1.25 micrometers, 1.39 micrometers as shown in figure. So this electronic dispersion of light, which is basically due to the presence of OH minus ions in the fiber, which are exist in the preparation of optical fiber. So by default it consists of this OH minus ions. This is happened in the preparation of optical fibers. Another absorption peak which is appears at 1.89 micrometers, it is in IR region. Another absorption peak which is appears at 1.89 micrometers, which is in IR region. The absorption of light is also due to the presence of transition metal ions like chromium, copper, iron. So due to these transition metal ions we have some absorption losses. So the corresponding graph, when we take lambda on x-axis and the fiber attenuation, it is its units are decibels per kilometer. The graph is appears like this, and in this graph you are getting here the attenuation losses, and these absorption values which are mainly due to OH minus ions which are present in the optical fiber, which are exist at the time of preparation of optical fibers. Second one is scattering loss. We know to vary the refractive index of the core and cladding, we are adding some impurities like boron, phosphorus. Such a type of impurities you are adding to maintain the variation of the refractive index of the core and cladding. But in case of core, actually the core is always having the same refractive index throughout the optical fiber, but it is not practically possible. So to maintain the proper refractive index, you are wearing some impurities. So some places the impurities concentration are more, some places the impurity concentrations are less. So the refractive index of the core is not uniform throughout the optical fiber. In some places the concentration is more, some places the concentration should be less. When the sending signal which is incident on such a type of concentration areas, then the light is scattered. Such a type of scattering loss is called Rayleigh scattering loss. And Rayleigh scattering loss is directly proportional to 1 by lambda to the power of 4. So from this equation it is clear that as the wavelength increases, the scattering loss decreases. So to avoid the scattering losses in optical fiber, you always try to send high wavelengths from one place to another place, then you can avoid the scattering losses in the optical fiber. One more losses are there which are called radiative losses, which are also known as bending losses. That losses you will discuss in the next class.